So welcome to the second lecture on point cloud registration. In today's lecture, we will cover a somewhat new framework for sensor registration, but mostly in the context of point cloud registration that we're interested in. I call it RKHs registration. It stands for Reproducing Kernel Hilbert Space. It comes from the kernel methods in machine learning. I don't expect you to know what it is, and I'm not going to teach you what it is by the end of this lecture, but you will see what are the things we can do with it and how to use it. If you're curious, then I will point you to more readings. So this is a framework that we actually use in the lab and do research. So in the previous lectures, I talked about some of the published work and established methods in the literature. Today is not so much for, I would say, educational purpose, but to give you an exposure, what is going on in the lab, what are the topics that you might see coming along more and more in the next maybe 5 years or 10 years with different flavors of the problem. So this is generally a context of functional registration. Functional in the sense that instead of working with data points that we directly measure at discrete time steps, we lift data into a continuous space, in a space that some sort of function is describing data as a whole, and then we can work with manipulating terms in the function space to find a transformation that explains the relationship between two sets of data the best. This is not the only way to go about it, but it is a very general framework, and you can have many realization and variation of this framework that I talk about. So the concept that we're going to cover, I'm going to rely on previous lectures that we learned the concept of manifold and Lie groups. But we will also review, and you see specific examples of it again. But generally, the space that we work on, it's a manifold. So the data points live on that manifold. An example of that is the familiar 3D space, where this manifold could be our familiar R3 when we had our point clouds in the previous lecture. So generally, we have a function defined on that manifold, and points are samples from that function. So for example, we have the first point cloud here, and then we have the second point cloud Z. These 2 point clouds need not to have the same number of points, nor we need to have the measurements of the same place in the space. It is generally the case that imagine you have a beam, a single beam that it moves in the environment, and you sense from the geometry. What is the reason we need to believe that as I move, I will sense exactly the same point in the environment so that I can find a relative transformation at 2 different time steps? That's not guaranteed, and in fact, this often is not true because of the variable density of the point cloud. The point cloud, as we move the sensor, such as LiDAR or camera, is at best a discretized sensing of the geometry as we observe. So that is a fact. But also, the number of points in practice are not the same. So there can be a lot of points that are not valid based on different conditions in practice. So the general setup is that we do not get the same number of points. In ICP, what we were doing, we were solving an association problem to make sure we have the same number of points to be associated. Then we would go ahead and calculate the residual and then solve an optimization problem. In this framework, we will formulate the problem such that it is correspondence-free. It doesn't need association, whereas association is built into the problem formulation. So instead of iterating over association and solving the problem, we solve the problem one time. The association is a byproduct of solving the problem. And that leads to two narratives in the literature. Should we solve the correspondences and then solve the problem? Or should we solve the problem and the correspondences are the byproduct of solving the problem? The mainstream thought is that we should, which has been around for more than 30 years, we should solve for correspondences, extracting features, solve the association, and then formulate the problem and solve the problem. And a lot of different challenges associated with solving the data association, robustness issues, and so on. Another narrative that I personally subscribe to it, this is from my research, and I think that's a natural direction to follow, not to replace the other narrative, whereas to cover an unexplored territory and see later what is the more general framework that covers both of them, is that we should solve the problem first. The association will come out of it for free. Now, within this framework, this is very aligned with another middle point in literature, which is similar to the expectation maximization framework that I pointed out in the previous literature, where the association are soft association, many-to-many association within the framework. And that is why, at the end, we know the association, because we can see which ones are highly correlated, or they have the highest amount of weight in the sense of dot product. So we could easily pick them to be the correspondences. So this framework, in that sense, it is somewhat many-to-many association, but it is built into the framework, and we do not need to run nearest neighbor for search. Although in the code, we might do it, but in the formulation, you don't see it. That's a matter of data structure and implementation. So the goal is to find a transformation that when we apply it to this function, it results in to the matched part for the overlapping part. There is a non-overlapping part that we do not know. So the framework is able to handle unknown correspondences, variable number of points, partial overlap, and as we will see, it works on different setup for different manifolds and Lie groups, but also it gives you an integrated model for incorporating color and semantic labels, unlike previous methods that are not so natural to integrate semantics and geometry. This model comes with a natural integration of both methods. So some background. As we talked about it before, for us, a smooth manifold is any shape that doesn't have sharp edges. It's a surface, and locally, when we look at it, it just looks like Euclidean space. It's a flat space. In other words, not bothering you with the formal definition of the manifold, there are local patches. If you chop it, you can flatten that part, and you can define local charts, coordinate charts, and basically treat it as Euclidean space. And the chopping is in a way that at the boundaries, there are some overlaps, and these local coordinates are compatible. We're not going to face any issues if we change the way we want to parameterize. For example, Euler angles, you have many options, z, y, z, x, y, z. You're not going to have problems switching between different choices. That's just a different way of dealing with local patches of the manifold. The examples of manifold are a typical Euclidean space, Rn. Any two-sphere is a manifold. It's a two-dimensional manifold. Torus is a manifold. Torus is built by two circles. So circle is shown by S1. Torus is Cartesian product of two circles. In general, tori is Cartesian product of n independent circles. So imagine you grab this smaller circle here and then move it all the way around the other circle. That will create a surface, and that's torus. So another preliminary that we need is the concept of inner product space. The inner product is the generalization of dot product. A vector space, V, it can be equipped with an inner product structure such that the properties of that inner product are that it's symmetric. That means the inner product of xy equals yx. An example of it, again, is dot product, of course, satisfies this. It is bilinear in both arguments. If you multiply an argument with a coefficient, you can just bring it out of the inner product. If you have x plus z, again, because of linearity, you get inner product of xy plus z times zy. Now, if the inner product of x with itself is calculated, it's always greater than 0 unless x is 0. In fact, every inner product space induces a norm which is defined using that inner product. So the norm spaces are more maybe general version of inner product spaces, but every product space is also a normed space. So the concept is, although we're going to work with the inner product of functions, the concepts are the same. If the inner product of two vectors or functions is 0, that means they are orthogonal. They do not have a common direction in the space. They're not pointing in any common direction. The higher the value of this inner product or dot product means they're more parallel, to the point that if the vector is the same, that's the maximum value. It's exactly parallel. But of course, depends on the magnitude of the vector as well. So we will see how we use this concept to formulate the problem. So examples of what things we can do with this framework before making you exhausted with some equations. So we can solve RGBD registration. What does it mean? We have 2 point clouds, target point cloud, based on the same terminology we used last time. We have the target point cloud X, and then we have the source point cloud. Each point cloud consists of a set of 3D points as well as color information. Color, you could think about it as 3 vector, RGB, HSV, whatever color space you like to work with. So we have a 3 vector of color and a 3 vector of position for each point. The collection of them will give you this set X as the target point cloud. And the collection of the other set will give you Z as some sort of labeled point cloud, because every point comes with a label, and that label is the color. It could be other properties. Another question is, what is the transformation, a rigid body transformation in this case, as part of, this is the same thing as SE3, that aligns these two clouds the best? This is the same problem as last time. It's not different. But unlike ICP, again, we want to work with a framework that works with the variable number of points, takes into account that the point clouds can have variable densities. They're not, even when the associations are perfect in the sense of nearest neighbor, they do not need to be the exactly same measurement of the same place in reality, and that's the problem. The best association is not even the true answer. So that is a fundamental limitation in the previous approach. So let's say we have a Kinect camera, we go around and we can just track using frame-to-frame accumulation of this registration. Here is a comparison that with respect to the ground truth here on TOMB dataset, we can track very well. Tracking is almost matching the ground truth. The baseline is a very successful method called direct visual odometry. In some sense, it's similar to this method because directly consumes RGBD data without feature extraction. It is from a family of direct methods. But it's solving the problem using a least squares formulation, which relies on some notion of association. In the next lecture, I will teach you the derivations of DVO and how we can register RGBD using least squares. This is still a very valuable method in practice. But what we talk about today includes that. You can reduce this method to DVO. Another example. On the left side, I have two circles. So the previous example, the manifold was R3. In this example, and the Lie group we were using for registration was SE3. In this example, the manifold is circle. What is the Lie group that is aligning this red set and black set on the circle? SO2, right? So it's the circle group. So the Lie group is acting needs to be the symmetry group of the basis space. It leaves the circle unchanged, but it moves the point clouds on data space. In the same way, the rigid body transformation is a symmetry group of R3. So the points at the solution, as you can see, they're not perfectly aligned. So the method is not trying to match points. It's looking at the entire set of points as a function and how they're best aligned overall. And that's a much better notion of alignment as opposed to trying too hard to reduce the distance of certain correspondences to 0. That will not serve our purpose well here. Now, this is obviously a toy problem, but what is the real world example of this circle registration? Does it look like a clock? How about clock synchronization? Imagine I have two processors, two computers. I can measure time on each of the computers. And I know the clock frequency on each digital computer. I press some button and record a sequence of time, right? And with some delay, I press button and record time. I know there's an overlapping part, but there's a beginning and ending that they might not overlap. Now, I want to find a delay between these two systems. If I know the frequency, I can map the time to phase, and then my problem is registration on the circle. So I should be able to perform clock synchronization only if I know the clock frequency of each computer. Now, it seems very doable. I haven't done that. It should be easy to test on two Linux machines just recording time. In the same sense that you can work with tori, many circles, it might work on a network of basically clocks. It's possible. I have not done it. Feel free to try it. Sounds like a fun problem. Now, if you have torus, imagine the base space now is a torus. I have a particular shape, a star here. Now, remember, the points live on the manifold. The points live on the torus. You cannot move these points in the outside world, in the ambient environment, right? Points live on this shape, manifold. They do not live in R2. So we're only allowed to move these shapes on the surface until they are matched. So we can handle that, and you can see here they are aligned. Again, they're not aligned in the sense that points are perfectly matched, but the shapes are matched. And the name of these methods correctly from old time in literature is shape registration, because the goal is not point registration. The goal is recovering the shapes, registering two shapes. A more interesting example, imagine I have images of a planet, which we can get from satellite imagery. I want to register these images to reconstruct maybe certain maps. The colors could be height or some other properties. So in this example, we're getting the map of Earth, and then, so this is, the first one is some contour map on Earth. We perturb it, so the manifold is basically the circle, right? The circle is not the same as two independent. The sphere is not the same thing as torus, right? This is S2. So the surface of this ball, Earth, is the planet that we're doing registration on. Then we perturb it using what map? In 3D, the circle becomes sphere, so we have to rotate this using SO3. So our transformation here, we can only rotate. Translation doesn't have any particular meaning here. We perturb it, and then the third one, what's happening, they are aligned correctly, right? So we have example codes, you can look into it. But we're able to solve this problem as a toy example.
In this application, what would you do about the fact that the Earth isn't a sphere, but an ellipsoid?
What do we do about the fact that Earth is not a perfect sphere?
Yeah. Like, so we have SO3 for rotation, which preserves a sphere.
Mm-hmm.
But the Earth is often modeled as an ellipsoid.
Now, this is a toy example, right? But let's say in practice, we're dealing with that challenge. We're actually working on a project. We have to solve it. One option is to ignore, see if it gives you a good answer. The other option is, now the problem is if the manifold is ellipse, as I will itemize the problem formulation, there is an inner product that can define the curvature of the space. If it's an ellipse, the curvature of the space will vary. It's not uniform like a sphere. So that inner product will help you to calculate a gradient that guides you along the ellipse. So it gets more technical, but if we are solving it using an optimization and we're using the gradient is responsible for following the flow correctly on that manifold surface. The more complicated the shape, the metric that we need to define the gradient will be a little more complicated. So as long as it's a smooth manifold, we can solve it. That's not a problem. But of course, I'm not talking about real problems, right? These are toy examples, conceptual. Hopefully, we will see some future results in these areas. Another example, what's the space here? The Lie group is SE2, the manifold is R2, right? Right, we can rotate and translate now. So we have two smiley shapes, two faces. Initially they were separate, and then we registered them by finding an SE2 transformation. Again, they don't have the same number of points. You see that there are areas that it's actually only blue. But overall, the shapes are matched correctly. Now, what you see in figure 1 and 2, at the solution, we calculated the Hessian, the second derivative of the cost function, the objective function, with respect to the transformation. In this case, the Hessian, which if we're working with a twist in R3, right? Or you could say twist is in SE2. Hessian will be a matrix that maps a vector from R3 to R3. This will give us a 3 by 3 matrix. Not fun to calculate, but possible to calculate by hand. So that will give you an operator, a matrix that maps vectors from R3 to R3. Then take the eigenvalues of this operator, the weakest eigenvalue as a vector field, which what we do, you take the lambda 1, and then put it in the, because remember, the eigenvalue of the Hessian is some vector like twist. Then put it in a basis of the Lie algebra, then generate a bunch of points in R2 as homogeneous coordinates, and then apply this vector field to all of these points. It will generate this vector field for you that you see. All these vectors are moving around. So the vector field related to the weakest eigenvalue is describing the symmetry of the shape. The most symmetric way is if you rotate about the central axis. So we're learning about the symmetry from geometry, the second order derivative. The strongest vector field corresponding to the strongest eigenvalue describes the direction that you will probably break the symmetry the most. If you move along these vector field, you create the biggest amount of difference. Some interesting and not so explored observation. So that was all motivation. Should we continue, or it's enough? If you're not sold, we shouldn't continue. We can just practice driving some Jacobians instead. And Lie group. Anybody interested? No? All right. So we all agreed that problem formulation is more fun than driving the Jacobians. So the general framework, we want to keep it general because when we see a problem, we create an instance of this framework and then we apply it. That gives us a framework to organize our thought and solve a range of problems instead of just formulating a single problem. We define this continuous sensor registration framework. It's as follows. It's non-parametric because we will construct our functions using data. We will not create a parametric model such as lines or polynomials or planes. We will not work with any particular shape, but we can model any shape. In the same sense, when we solve the linear regression problem with Gaussian basis, we could regress any function, but we never specify what's the order of the polynomial. This is doing something similar to that. So the sensor registration problem is defined as a 5-tuple. First thing we need is a Lie group, similar to the examples we discussed. Then we need a smooth manifold. Then we need the action of the Lie group, smooth action of the Lie group on the manifold. It needs to be a diffeomorphism. It needs to be differentiable, which is Lie groups act smoothly. Usually it's not a problem when you rotate and translate. That is satisfied, usually. So in the same sense that when we rotate points on a circle, we can act on it. That's what it means. Then we need an inner product in the Lie algebra. We're not going to explore it much, but this is a technicality because we need to derive the gradient. If you want to use, for example, gradient ascent or descent to solve the problem, we need to derive the gradient. This metric describes the structure of that manifold. However, because we're solving for the transformation, it needs to be defined in the Lie algebra. Why didn't we define an inner product in the previous lecture? We just linearized using first-order approximation of the exponential map, and then we derived the Jacobian. We never talked about a metric. So that's the weird thing that we can do. We can derive gradient and Jacobian as in a metric-free sense on Lie groups using a matrix exponential. That's somewhat nice because you don't need to think about a metric. A more general version of that that is also doable on Lie groups is how we calculate the gradient in Riemannian geometry. For that, you need a metric because the differential of a function along a vector x is the gradient, is the inner product or dot product of the gradient with some direction, vector. The differential does not need a metric to find, that's the delta of the function. Mathematically speaking, the gradient needs this metric. You need a metric to tell you what is the magnitude derivative of your function along that direction that gives you that differential. Based on how you choose this metric, it can change the gradient, right? And typically it's chosen in a way that describes the geometry of the space you work on it. The simplest way is, what is it? It's the dot product that we use, right? When you do Taylor expansion, we use the dot product. This is a generalization of that. So the last thing we need for this 5-tuple is a kernel. A kernel is a symmetric positive definite function such as that Gaussian kernel. We'll see why. This is for the geometry. Then we need 3 items for the information space so we can encode something like color or semantic labels. The information space itself is a 3-tuple such that it has an inner product space. For example, color. The color that we see, let's say C1, C2, right? They have RGB vectors, and then you can define the dot product or inner product of C1 and C2. So the space of all 3 vectors as colors and their dot product will give you this inner product space. But we want to keep our options open. It doesn't have to be color. Any label that you want. Maybe you learn features using deep learning and you want to use that. That's also possible. So we keep our options open. We're not limited to the dimension of the label. It can be 10, 100. You can potentially scale the dot product, right? It doesn't have to be just the plain dot product. It's up to definition. Now, on top of that, each set of points come with labels. What it means is that there is a one-to-one correspondences between points in the geometric sense and their associated labels, which is interesting enough that RGBD cameras are giving us that. Every point is coming with an RGB. There is a sensor that physically is satisfying these conditions, which makes it very interesting. So what it's saying is that we need a dense set of labels. Each point should come with a label. And this L is describing that. Now, once we have these, we can use G1 to G5 generally to build a gradient that will allow us to solve the problem in the sense of geometry. I1 to I3, it allows us to encode the information in the point cloud. Now, without telling you what is an RKHs, unless somebody asks, that kernel, if it's positive definite, a positive definite kernel is a kernel such that when you evaluate this, it's a generalization of positive definite matrices. The kernel is positive definite. When you evaluate this, it's positive. Now, if your kernel is Gaussian kernel, some length scale, of course, it's always positive. The coefficients, they don't have to be positive in general, but let's say if they are positive, well, it's always satisfied. Colors are always positive, right? That dot product of two color vectors will be always positive. So generally, this is satisfied, but the kernel must be, technically speaking, positive definite. And of course, it's symmetric. It doesn't matter if we evaluate k of xi xj or k of xj xi. Now, given a positive definite kernel, we can define a vector space of function called reproducing kernel Hilbert space. So we define the inner product spaces. Hilbert spaces are inner product spaces that are complete. So any inner product space, including our n with dot product, is a Hilbert space if it's complete. Completeness means that it contains all its limit points. Every Cauchy sequence that you define, it will converge. In that sense, the space is complete. Nothing weird will happen. When you take the derivative, you calculate the limit. It includes all its limit points. You can always complete a vector space to make it a complete inner product space. So these are matter of technicalities, but that's the structure we need. So a reproducing kernel Hilbert space is a more special type of Hilbert space, where you have a kernel such as this that acts as evaluation functional. Because the vector space of function is not a space that you can point evaluate functions. It's very abstract. You have a vector space, its elements instead of vectors are function. We do not know how to evaluate those functions necessarily. There's a structure in if I show it like this, RKHs that allows you to evaluate your function at a particular point by taking its inner product with the kernel. A familiar example of evaluation functional is the delta function, right? The integral of delta function with any function, it will result in the point evaluation of your function. F of x, delta x minus a d of x, that will give you f of a. So delta is evaluation functional, and in fact is a very special case of this RKHs. You could choose your kernel to be delta. It's just not as interesting because it is just a point, whereas this Gaussian kernel, it covers a neighborhood. We can talk about correlation in a neighborhood as opposed to just a single point. So this kernel is a more general version of that delta function in that sense. It allows you to evaluate your function. Together, that is called RKHs. The entire kernel methods in machine learning is built on this space. Well, not all of them, because some of them, they do not need the kernel to be positive definite. For example, support vector machine. And a lot of methods on kernel machines are built in this space. Gaussian processes, they're operating in this space. So an interesting result is that it was proved first around in 70s and 80s, later in 90s, again, with a simpler proof that if you try to minimize any cost function that is also regularized in search of a function that describes your data the best, not to fit a function, search over all class of function that describes your data the best in this space, what you will find, this is proof, this is a theorem, that your function always will be in this form. It's a weighted sum of some coefficient times the kernel. Every kernel is centered around one data point. If you have n data points, the best function that you can find that minimizes the regularized cost admits this representation. So this is very powerful because we know that we need to work with functions that they have this structure, weighted sum of some coefficients times the kernel. And we're going to build on this result to form our functions. So the goal is to give me a giant point cloud, and I will turn that point cloud into a single function, one object that describes every point on that surface, if you will.
Is this representation still non-parametric? Or?
It is non-parametric because we do not describe any shape.
Okay. So I'm misconstruing the fact that there's a kernel that exists. I'm misconstruing that as some sort of parametric representation of the function itself.
Well, that alpha is a parameter that if you build your model such that you're supposed to find that alpha, then you could call it parametric. For example, in Gaussian processes, that's non-parametric. You can still write it that way. But it's not so much we're after alpha, because alpha just has a formula based on the kernel itself. So both of them are possible. But generally, this is called non-parametric representation of the function, because it has as many terms as your data points. The more data points you collect, that n, right, this sum will grow. In theory, the Hilbert spaces, the inner product of functions, are infinite dimensional vector spaces. However, as a result of this theorem that needs a lecture on its own, is that we can work with a subset of the space that is only spanned by data points, yet we can represent the function. This is very magical because now we can solve problems using the data that we receive as opposed to dealing with infinite sum. These are all wisdoms before deep learning. Then I'll point out how it's connected to deep learning. All right, let's now turn the point clouds into functions without pain. You can forget everything I said, just do this. Pick a kernel, Gaussian kernel, for example. Your function will be weighted sum of these labels times kernel. Now the labels are vector. That's okay. You can keep the labels as vectors. And the kernels are centered around each point. Remember, the labels L sub x of xi means the color of that point, for example, right? It varies based on the point, but it does not vary based on the transformation. It's fixed as you rotate or translate. Also notice that we're not normalizing. So because we're not going to query functions, we don't need to normalize. If you wanted to actually, because it's a function, query the new value in between to interpolate, then there's a need to normalize in the sense of kernel density estimation, so to make sure we're not adding all the neighbors to get a bigger value. It's not necessary to normalize because we're not going to query the functions.
What's the meaning behind this notation for the kernel in this blue box where you've got one dot and one thing that's actually there?
Well, the dot is the variable. Because xi is a 3D point that we received in the point cloud. The other one, we should write a variable, anything. Let's write, maybe we could write, let's say z. Or we could call the basis z and keep it x, if you like to write f of x. Or maybe y is better because I'm using z for the second cloud. So y can be any point. Now it's a function, you can evaluate it at any point. So we do the same thing for the z cloud. Now we turn the entire point cloud into a single object with as many points as we want. Now one reason we need this structure of inner product space because we need a reason to talk about alignment. Alignment geometrically is tied to the angle and how parallel are two vectors. These vectors can be functions. And the inner product or dot product is a natural tool for that. That's why we need the inner product space. So we define the inner product of our functions to be like this. This follows from that RKHs space. It comes with this definition of the inner product. So the inner product is such that we take the dot product of labels. That will give you some scalar. Let's call it Cij. And remember, this is a double sum over I and j. And the kernel evaluated at the basis of two functions, xi and zj. Now, it is a double sum because for every xi, we should loop over every zj. Okay? If you have 2,000 points in the first cloud and you have another 3,000 points in the second cloud, the total sum will be 2,000 times 3,000, which is 6 million terms, right? It's insane. So we lifted the problem into function space. Typically this happens. The problem basically blows up and it becomes super large scale. Is that any better? No? You're giving up too fast. At first look, it's not, and that's what the reviewer of the paper we wrote first thought, because we didn't mention it explicitly. It was somewhere in the paper, but it wasn't explicit. This would not be attractive computationally. However, this is a sparse double sum, because this kernel, it's only valid in a small neighborhood. There are only so many points in the second cloud that falls into the bandwidth, this shape of every kernel term. So you end up with some local terms in this double sum, which if you evaluate this as a matrix, it's in a I have it in a figure, I forgot to include it. This will be the dimension of this matrix, right? This matrix will be sparse. You get some of the, terms are non-zeros, most of them are zeros. Besides, you can control that. You can make this kernel using its bandwidth to be very sharp. Then it will become sparser. If you want to include more points, you can increase the bandwidth. So it's a trade-off. Generally, more bandwidth is good because you correlate more points in the neighborhood, but of course, it's going to make it slower. So it seems to be quadratic, but because it is sparse, it's somewhat like linear time, roughly. So it's pretty good. In practice, you can calculate it. In the latest library we have, we do this on GPU. So it's very fast. So we're ready. We have a metric that measures the alignment of two functions. Let's maximize the dot product or inner product of these two functions when a transformation such as h is aligning them. How this transformation acts on a function, we do not know yet, but it is possible to talk about it like this. So the goal is to maximize the inner product by searching over a transformation that is on a Lie group such that these two functions are aligned. If they're aligned, the angle between them is minimized. So the angle between two functions is similar to how you write the angle between two vectors. Now, if the transformation is an isometry, that means it does not change the scale. It's not going to scale, right? It's a rigid transformation. What happens if the transformation is an isometry, it will not change the norm. Because it does not change the norm, then basically this denominator, right, will be independent of h, the transformation. So we are actually minimizing the angle between two functions, or maximizing its cosine. Same thing. But because the transformation is a rigid transformation, in this case, we can just go after maximizing the inner product. However, if you work with, let's say, SIM3 group, you need to go back to this formulation. That's because now we're scaling as well. So we successfully constructed problem. All the story is that now we have a problem. If we can solve this, we get the transformation. At this point, it doesn't matter what it looks like or what the space is living on. It's just an objective function with some decision variable. So the objective function f of h is this. Some constant Cij, these are dot products of every color in the X cloud with every other color in the J cloud. However, if the kernel gives you 0, then you don't need that in the sum. Another magical thing is that the transformation that acts on the function that we do not know what it is, it induces the same transformation inverse of the same transformation and the input. This is very important because otherwise we have to work with this operator. This transformation that acts on a function is an example of an operator. If these functions are generalization of vectors, you can think about the operator as a generalization of a matrix. Matrix is a finite dimensional operator. What are the examples of infinite dimensional operators? Differential, gradient, that Nobel operator, integral. For example, I define an operator to be the second derivative with respect to time plus some constant, positive constant. That's it. Now I'm going to talk about the position function of a particle that is moving along some x-axis. The differential operator acting on x will give me its equation of motion if it's not forced. Right? This is a second order differential equation for mechanical system you define. It comes from this differential operator. Similar way you can define integral operators. But anyway, we don't want to go that way. It seems too hard. We're not trained for that. If you are, give me a call. We decided not to go that way. So luckily, from representation of theory of Lie groups, we have this result. That if every Lie group can act on, typically, roughly speaking, on any vector space of any dimension. However, this result holds. Now, to see this y in a very, very naive and simple way, imagine I have this line, y equals f of x, and I'm going to apply the transformation to the outside, and I'm going to write y plus 1 equals f of x, right? I'm just applying a translation as the transformation, which is, of course, this is x, just a line, same as y equals x minus 1. Now, both of them, doesn't matter if it's y plus 1 equals x or y equals x minus 1. At x equals 1, it crosses the line and you get this you have to lock it. We get this line. Now, this is a very simple example, but shows this concept of linearity. When it's applied to the output of the function, it induces the inverse of that transformation in the input space. This result is the same on stereoid. It's like Lie group on vector space of functions. Comes from a very advanced topic. We do not need to be worried about it. But this enables us to write the inverse of transformation here, which is nice. Now I can just go ahead and solve it. This is just like ICP now. It's just wrapped around the kernel, which we did that as well. We had that robust kernel. There isn't anything different here than a typical optimization problem. So we are in good shape to actually solve it. So let's make it more specific. Let's talk about R3 so things make sense. My kernel will be this Gaussian kernel. Some distance, you could call this, this is called signal variance, but some positive coefficient exponential of some distance of xy divided by some length scale. Maybe we could choose a different notation as well, that L is not related to these labels. The Euclidean distance is a typical choice, but you're welcome to change this distance if you want to for your problem. For example, in ICP, we had point-to-point, point-to-plane. In GICP, we had that probabilistic distance, which is in somewhat plane-to-plane, and other types of distances. So the color dot product, it will just give you something like R1, R2 plus G1, G2 plus B1, B2. RGB dot product that you read from images. In practice, we actually found it to be more useful to work with HSV color map, but that's just a side point. You get marginal performance improvement. HSV apparently is better. That was an advice from a colleague who works in computer vision. He said change it to HSV, you will get better results. And it did work. So maybe it helps you as well. If you have RGB, change it to HSV. Maybe it makes your results better. So the goal is to maximize this function to find the rigid body transformation. If I know the gradient, I can just do gradient descent. By following that direction, that will give me an ODE. The steady state solution of this ODE will be at this steady state, H dot is 0. That's the necessary condition from calculus. So the necessary condition is that the gradient must be 0. And if I have the gradient, I can do gradient descent like hk plus 1 equals hk plus alpha times gradient, right? Which we talked about it before. The continuous time version of that is this ODE. If you don't remember, we can write it like this. On the left-hand side, as alpha goes to 0, is in fact h dot. So Euler integration is just one way of doing it, which we will not do Euler integration because it's a Lie group parameter. We cannot add the delta term. So because we're maximizing, we're doing gradient ascent. Of course, we could multiply a negative sign, and then you would do gradient descent. This is, let's say, the simplest solver that we can build. and that's what we're using here. You could do better probably, but that's the simplest solver because we only need a first order derivative information. And we talked about it that because these contours of the function, these level sets are constant, the function does not change, the dot product of the gradient with any delta movement along that curve will be 0. If the gradient is not 0, the only explanation is that the gradient is orthogonal to level sets of the function. So it's the maximum direction of the maximum ascent towards the peak here. So we're going to do gradient ascent. There's several pages deriving the gradient. I'm going to spare you. Nobody has the patience to listen to that. So we're going to ask some friends. They're good at math. This is the gradient. And it is the gradient if your kernel is Gaussian and you're working with this SE3 transformation and R3, right? So you could, within this setup, you can change a lot of things, and it's still the gradient is the same. So that's pretty cool. This is my twist. This is the gradient at the identity, but you know that when I move in a Lie group, we learned that the differential equations becomes like this because we have to transform the tangent vector to the Lie algebra, right? This is actually like this. And the way you can see that is, let's say H is, T is the translation. We have RT01. So I have RT01 times omega and V. So what happens, we only need to rotate, which will give us the general differential equation, the reconstruction equation for SE3, right? But we can write it for rotation and translation separately. So moving in the manifold from one point to another point, it just needs a rotation. When you look inside, in general, you could just write it like this and ignore it. If you look inside, we're just rotating the vectors. It makes sense because translation will not change where we are. It's not going to change the magnitude of the velocity. But what direction we move, it will change the magnitude of the velocity. And that's what we see here. So we know the gradient, and this is nothing but the reconstruction equation of Lie group. I should actually use small h, which is exactly what we use here. So we compute the flow. Now we need to integrate. We talked about this endless times that never add them because it's an element of the group. Just like you did in your homework, we have to integrate. A simple integration that is in fact exact is using the exponential map. we could introduce some step size. Right? Because you might not want to take the full step with the gradient. Usually it's a very bad idea in optimization, especially for gradient ascent or descent. So ultimately, the exponential term will give you a delta rotation and delta translation, whatever that is. The gradient along some direction with some step size, it tells you that do a delta rotation, do a delta translation. Multiply them using matrices, that results into the integration rule that we need. So rotation is accumulated by multiplication. The translation is the previous translation plus rotated version of delta t. That is compatible with SE3 group that we deal with. That's it. So we formulated the problem, we solved the problem using one instance of solvers. Does it work? We did all the work. The question is, does it work? Of course it does. I wouldn't waste your time. I would never do that to my beloved students. Let's see what Ray says. I think he talks in this video.
CBO, a new framework for registering semantic point clouds.
This is an extension of the work. Now we're going to bring in the semantics.
Range sensors like stereo and
Oh,
have been found in many
no, go back.
modern. I'm going to introduce semantic CBO, a new framework for registering semantic point clouds from stereo and RGBD cameras. Range sensors like stereo and RGBD cameras can be found in many modern autonomous robots. They're heavily used in localization and mapping algorithms to generate the poses at different timestamps. These range sensors can provide rich information, not only the geometric measurements, but also the color
Is it
or
too
even
fast?
semantic information as well. The main question is, how do we combine the semantic and
That's how you
geometric
watch my
information
lectures,
into
right?
a unified model that works better in practice? Especially, we are interested in the point cloud registration problem, which is the building block of many 3D computer vision and SLAM systems. The point cloud registration problem
My job is to distract
estimates
you from
the relative
watching,
pose between
actually
two
learning
successive
from this
point
video
clouds.
by talking.
But it is a hard problem because the observations could be pretty noisy. The two point clouds might just partially overlap. The scene is textureless. There might be different densities of the observations, and there might be some dynamic objects in the scene. Existing methods usually formulate the problem as some optimization problem. Different methods might have different representations of the point clouds, and then the cost functions are defined accordingly. Iterative closest points is a very famous point cloud registration problem. It relies on one-to-one data correspondence and represents the point cloud as a discrete set of points. The cost function is minimizing the pairwise geometric residuals. It is possible to incorporate extra color or intensity information by adding the regularizers for these colors. EMICP differs from other traditional ICP in that
We covered this last
data
time.
correspondence as a hidden variable, and then use EM algorithm to infer it in the middle. However, parameterizing the correspondence could take a lot of time. Normal distribution transform is another class of point cloud registration methods that works very well in practice. It represents the point clouds as voxels of Gaussian distributions. And the cost function is basically the maximum likelihood, fitting the observations of the second point cloud into the distribution of the first point cloud. However, efficient and accurate discretization is challenging. In this work, we propose a new point cloud registration method that is continuous, that doesn't rely on one-to-one data correspondence, and it is easily extendable to non-geometric information like color or semantics. Let's go back to our basic problem. We want to find a good representation for the two point clouds x and z. and we want to define a suitable cost function for them. Finally, we want it to be data association free. The 2 point clouds representation should include both the geometric and color semantic observations. Here's an example from the Kitty dataset. Let's pick a single point xi from the stereo observation. This xi has the color pixel, which is basically a 3-dimensional vector. We also have a corresponding semantic observation from some neural network, and it has a different dimension than color. We combine them with the tensor product. And this is what we call the hierarchical semantic representation for a single point x, or we can call it as a label. So this label will encode the non-geometric information for a single point. Besides the hierarchical semantic information, we also encode the geometric information with a square exponential kernel. This kernel will have larger values for points that are close, and has very, very small value for points that are far away. So we do this for all the points, and we obtain a function representation for the entire point cloud, fx. It is essentially a weighted sum of geometric kernels, while the weights are the labels. Now that we have the continuous function representation for the point clouds, we want to define a cost for it. We want the cost to avoid the explicit hard data association. The cost function should measure the alignment between the 2 point clouds. For vectors in the inner product space, we can use the angle between them as a measure of alignment, and this also applies to point cloud functions. So here we define the cost function as the inner product of the 2 functions of the point clouds. The nice thing about this cost function is that it avoids explicit hard data association, and we're actually aligning the 2 functions instead of 2 pairs of points. After some math manipulation, we'll arrive at the double sum of geometric kernels, where the weights of these geometric kernels are the visual features. So this objective function will contain the information from both the geometric and non-geometric information. We want to perform the gradient ascent to maximize this objective function. A nice byproduct of this cost function is that, similar to the normal vectors, we can use the cosine angle between these 2 functions to measure the alignments of these 2 point clouds. Below is an example from the Kitty dataset, where we change the homogeneous transformation by rotating.
Notice the convexity of this function angle when it's represented against normal angle and distance.
Distance is 0. This indicator
Here in the bottom.
will have larger values. So to sum up, we will propose a framework for registering hierarchical semantic point clouds. The point clouds are represented as continuous functions that takes the geometric and non-geometric information into consideration. And the registration problem is formulated by maximizing the 2 functions. In our practical implementation, the computation for the double sum might be costly. So we downsample the points with OpenCV fast point cloud selector. Also, we compute each element in this double sum in GPU in parallel in order to speed things up. Here are our experimental results. We evaluate on both an outdoor and indoor dataset. Kitty is an outdoor dataset that provides the color stereo cameras. It has multiple sequences with ground truth. And error was evaluated by translation and rotational drip per 100, 200, until 800 meters. The Kitty stereo point clouds are computed via ELIP-ELAS. As you can see the picture on the right, it provides stereo point clouds, but there are still noise from the color and geometric. And also, we get the semantic observations from the neural network, but still, there are some noise visible. Here is an example of aligning 2 point clouds. The first one is in orange, and the second one is in blue. Here's another example in the Kitty dataset sequence 3, and in this example, we want to align the entire sequence frame to frame, And the curve in the middle, in green, is the accumulated trajectory from our frame-to-frame registration. The point clouds are stacked together based on the transformation from our algorithm.
So this is not
algorithm
SLAM.
will take both the
It's
semantics
just
and
accumulation of
information
frame-to-frame
into account.
registration. It will drift.
This is a close look at the stacked point clouds. Still, the green trajectory is in the middle. And we can see that the roads are pretty clear. This is a qualitative comparison between the proposed methods and several baselines. The ground truth is the black dashed curve. The three solid curves are the proposed methods, and the dot dashed curve are the baselines. This is another sequence with a similar comparisons. Still, the black dashed curve is the ground truth. The solid curves are the proposed methods, and the dot dashed curve are the baselines. This picture shows that the proposed methods have lower drift at both at lower and higher speeds, while some baselines might have higher drift when the speed goes fast. So this is the quantitative result. When using both color and semantic information, the proposed method will have the lowest translational and rotational drift. TUM dataset is an indoor dataset that uses RGBD cameras. This sequence could be challenging because it includes some non-structured, non-texture environments, and the observations could be pretty blurry. Here's the example in a structured but non-textured scene. Still, our trajectory from frame-to-frame registration is highlighted in green, and then we stack the point cloud based on our registration result. As you can see in the map, the scene is pretty featureless, and it can be challenging for traditional registration methods. In the quantitative result, we can show that our geometric results are comparable or better than geometric baselines, and our color results are comparable or even better than the color baselines. So to sum up, we propose a novel point cloud registration method that represents hierarchical point clouds as continuous functions. We introduce a new way to measure the alignment, and we demonstrate comparable or better performance versus baselines. The code is released open source. Any questions is welcome.
You can talk to Ray if you have questions. So Ray took the time and implemented this on GPU. There's a CUDA code. Depends on how many points you use, but I think it works on Inception. Going layer by layer inside. Mobile robotics. He implemented in GPU, I think, something between 5 to 10 hertz we could run it. So it's real time, but it also depends how many points you use. With 2,000–3,000 points, it works well. But also notice that the stereo point clouds in outdoor are extremely noisy. This results using that type of point cloud is very surprising.
So in the start of the lecture, he mentioned that this can be used to avoid for dynamic cases, dynamic environment cases. So like, do we need to segment it, or does this handle this?
The question is, I mentioned we can handle dynamic objects. I did not mention that.
I don't know, in the video.
In the beginning of the video, it mentioned that dynamic object can cause problem, but this framework is not explicitly dealing with that. So that if the object is moving and is super close to the camera, it can cause a serious problem because the moment it's gone, the point clouds you see are so different that it becomes an outlier. That's a problem. So now, some open problems. So you could see that we extended using tensor products to include color, intensity, semantic labels from deep learning. So if you learn features from deep learnings, as long as they're not dependent on the transformation invariant, you can easily use them as labels for your points. That's possible, and it's interesting. We used fast feature detector from OpenCV. Again, if you can replace that front end that tries to downsample and select key points using deep learning, that's very exciting because then we have key points, not necessarily high quality like feature extraction, but it's a semi-dense structure of the points we see, so we can track. That will be interesting as well. This is an example on torus. If we cut torus and open it, then we can look at it as R2, because torus was 2 circles. Cut it along that top area and then open it, right? Then look at it as an R2. So this is between minus pi, and again minus pi and pi. We flatten it and then because this is 2D, we can evaluate and visualize the cost function. We are only solving for 2 angles. With the objective function itself, that's a 3D space, we can visualize its contour plot. Depending on what you choose for the length scale of the kernel, in fact, you can make the problem convex. Here, 0.5 makes the problem convex. No matter where you start, you will find the globally optimal solution. Which is here, I think it's the same cloud, so 0, the center is the point that will maximizes the inner product. However, if you reduce the length scale, you can make the problem very complicated. You get many local maxima. I think we have a visualization of this. So as we reduce L, it does make the problem non-convex. Then it matters where you start your search, especially if you're doing gradient descent. So one open problem is that if I can dynamically choose this length scale, the hyperparameter, that at every stage of the optimization, it keeps it convex and gradually makes it more complicated as we get closer to the deepest minima or maxima here, then I can find a globally optimal solution. However, it's extremely challenging to do that. So what is the right objective function to handle that? That's the question. But if you choose the length scale large enough, usually it works well. But it takes more number of iterations.
Here the red dots are key points. The red dots are key points.
Red dots are, these are different local maxima. There's a function in MATLAB, it gives you all the local maxima of the surface. Now, a side note, you might wonder what's the relationship of this way of looking at the problem with existing works. I'm going to show you that we can reduce this problem to the weighted least squares. So generally, the kernel uses some sort of distance matrix. Let's say we work with the exponential kernel. Define this bandwidth times the label, some weights. So the inner product basically is the double sum of some weights times the exponential of negative of the distance squared. That's what we're dealing with. We're going to make 3 assumptions that will reduce it to least squares. If they have the same number of points, of course in the least squares problem, that's the case. And if they are ordered in such a way that they are associated. In the original problem, we don't need that. We don't care about the order of the points. If they have the same number of points, and if they are ordered that we know the associations, and if we basically ignore soft association and only evaluate this double sum for corresponding points between cloud X and Z, that will reduce the double sum to a single sum because we only need to loop over correspondences. Then the objective function becomes a single sum over some weight sum times the exponential of corresponding points. This is I dropped the second I for simplicity. Now do a Taylor expansion for the exponential. The first part is constant, of course. It does not depend on the transformation. The maximization of exponential of negative of this distance becomes minimization of this weighted least squares problem. So the weighted least squares problem is a special case of what we're doing. And in fact, there is something called generalized least squares when you deal with this soft association. Not necessarily kernels, but you do evaluate many-to-many associations. So this is important because we want to link it to other works so you know where we stand. So we are generalizing what we see in the literature. How can we solve this? If the weights are constant, it's just the weighted least squares. If the weights will vary, we can use IRLS, right? So now we can use second order solvers because it's easier to solve. Some open source solvers. So the initial version of this, when I published the work, is here. I do have a simple MATLAB class function. We can take a look. There's a C++ version of that as well in this repository. The GPU version, where it incorporates semantic labels, is in this repository. And this is for the journal version when it has examples for sphere, circle, and some other fun examples. This is indirectly related to this work. Min Khan, one of my PhD students, he used this idea to build a loss function to solve the problem of depth from monocular camera. Because of the continuity of the loss function, we can, as a result, we can get better results, but the message is that we can regress something like windows of a car, because generally other methods, even if they perform better, they miss transparent objects, because it's very difficult to get the depth value of a transparent object. Photometric loss fails in that case. So he's using that in 3D to enforce this geometric consistency in a soft way, and then as a result, we can regress windows of the cars much better. You can take a look at his work, and there's a video as well. If you're interested in this problem, you can, an exhaustive version of the work is in this 50 pages of written work. The second one, which I recommend looking into that, is what we saw the presentation of it. Ray, another PhD student in my lab, he's the developer of this work, which is probably what you might want to use in practice, is this work, not all the other stories that we talked about. This is the work for depth from monocular camera. The third one, now this is our recent attempt to use deep learning to solve correspondence-free registration. It only works on SO3. If you remember, I said when we know the correspondences, we can solve point cloud registration in closed form using Horn's method. And the way it works, it centralizes the point clouds, builds the cross-correlation matrix, uses the SVD, and then recovers the rotation matrix. What we're doing here, we're doing Horn's method in feature space. The features we learn are equivariant. They have the same rotation as the input point cloud. Therefore, in the feature space, because of max pool operations and some other operations in the neural network, we recover the exact correspondences if it's a copy of the same object. So we can apply Horn's method in feature space, which makes it somewhat better, because in the input space, we don't know the correspondences. Now in the feature space, we know. How it's related to this work? This could become the front end, or whatever you want to call it, but this can become the feature learner of this framework. Whether you want to learn features for appearance as labels, or replace the points that are input of the kernel. Because those points, so long as they have the same orientation and translation of the input points, then you can apply this framework on top of the features learned from an equivariant neural network. This is our current work. However, if you want to solve it for SE3, it needs to be SE3 equivariant. There are recent attempts, there are approximation versions of that. You can learn features that are SE3 equivariant, but mathematically that has a problem because there is no exact form for SE3, because SE3 is not, to confuse you more, there is no adjoint invariant inner product in its Lie algebra. Okay, so this should give you a flavor of what we actually do in the lab when we go to work. We don't work on ICP, but variants of ICP are useful in practice, and a lot of teams in DARPA challenge probably they used it, they built good maps. With good engineering, you can make it work. But this is somewhat the next generation of that. So that's it for today. And next time, we're going to talk about DVO. It's a point cloud. It's an RGBD visual odometry that uses least squares for solving the problem.